Assalamu alaikum, dear students. We're back with another video lesson. In the previous lesson, we talked about natural frequency. We said natural frequency is basically the rate at which a body oscillates when it is left undisturbed, when there is no force acting on it, let's say. That is the natural frequency. And or you can say one or two examples would be the swinging of a pendulum or the vibration, let's say, or the vibration of a guitar string, let's say. And then after that, we talked about a forced vibration. Forced vibration, and it is, as it is very clear from its name, it is a vibration that is forced, you can say, or something is forced to vibrate. That is basically what is forced vibration. Or you can say it is the oscillatory motion of a system caused by what? Caused by an external force. And of course, we did talk about some examples here. We said if we have, let's say, 4 pendulums, and these pendulums are attached with an elastic band, you can say here. So once, let's say, you give a push to one of the pendulums, let's say this blue one, and then of course this blue one starts to swing back and forth, right? But then you will see that soon after, the other pendulums start to vibrate with this. Why? Because part of the vibration of this pendulum would be transferred through the elastic band to the other pendulum. So the other pendulums start to vibrate because of the effect of this. So those that are vibrating, of course, because of this, these are called forced vibration. Why? Because these are forced to vibrate because of the pendulum that you just gave a push, let's say. And of course, here's the detail that we went through last time. And then after that, we said, by the way, and we also mentioned this, remember, when this vibration, let's say, or one of the things that the, let's say the intensity of a sound depends on, it is the surface area of, or you can say the vibration of the surface area of an object. In another word, the bigger the surface area that vibrates, the louder the sound becomes. And of course, we had this note, we said the bigger the body that vibrates, let's say, the more the intensity, and of course, the louder the sound. Why or when did we talk about this? We said if we have one guitar string, let's say, if you just plug it once, you would see that the guitar string would vibrate, but it is not that loud. And of course, the vibration would take a longer time, let's say, compared to if we, let's say, install or tie this same string on a body of, let's say, of a guitar. You would see that because this string is connected to the guitar, now the vibration of the string will be transferred, let's say, by the bridge of the guitar, of course, to the body of the guitar, or you can say more specifically to the hollow body of the guitar. Now the hollow body of the guitar vibrate, or you can say, forcefully because of the vibration of the string, or you can say the body of the guitar will be forced to vibrate. Now the whole body of the guitar or the hollow body of the guitar is going to vibrate. Now you have a bigger surface of vibration. Bigger surface of vibration, of course, it causes or creates a louder sound. But what happens in effect, you can see that the vibration of the string will die out way faster. Why? Because now this energy of the string or the vibration, now it is transferred more efficiently to the surrounding area using the hollow body of the guitar, right? So this is what happens here. So of course, because of that, you would see that when a string is plugged that is attached to a guitar would sound louder than just a string if it is not attached to the body of the guitar. And of course, we did solve or answer this question. We said, why does a vibrating string sound louder when it is on an instrument like a guitar than it does when it is stretched on a bench work, let's say? And the reason was because we said the vibrations are transferred to the instrument's hollow body, or could be the guitar's body, let's say. And of course, the body vibrates in a much louder volume of air, creating what? Creating a louder sound. And of course, a louder sound, you can say, increasing the intensity of the sound that is produced. And then the last thing that we stopped at was vibration of or at the natural frequency produces resonance. Now, what is the natural frequency? We did also talk about this. Let's say every object has a certain frequency that it vibrates with it, yeah? One of the easiest things so that you can imagine is, for example, pendulums. Now, we have, let's say, when we have pendulums of different length, of course, you would know that the length would affect the period. If it affects the period, that means also affects the frequency. So different length or different pendulums with different lengths have different frequency, of course. So we can say every pendulum, if they are different in length, would have a specific natural frequency. So when you just give it a push, of course, it swings back and forth, yeah? And of course, this swinging or back and forth, that is what we call the natural frequency, which is going to be different for another pendulum that is either shorter or longer. In the case of these pendulums, of course, you can see that each one of these pendulums, except then these two blue ones, of course, let's say this blue and then this and this, these are, of course, would have different frequency because they have different length. Different length, that would be different frequency. You can say the longer, and of course the longer the length, you can say the less the frequency. And of course we did talk about the equation or the relation why it is like this. Let's say we said period of a pendulum equals to a period equals to 2 pi square root of what? Of length over let's say gravitational acceleration of free fall, let's say. But then of course we can say frequency equals to 1 over the period. Yeah? So we can say frequency is equal to what? 1 over 2 pi, and of course we can flip this one here, so we can say G over L. So you can see here these two are inversely proportional. In another word, the longer the length, of course, the lower the frequency. So you can see here this one would have the lowest the frequency here, and this one would have the highest frequency when, let's say, when left undisturbed, let's say. Okay, so now, but these two, because they have the same length, so we can say they have the same frequency. All right, so what is, once again, what is the natural, or what is the resonance, yeah? So we can say resonance occurs when the frequency of the vibration matches the natural frequency of the system. Let's say we have a system, we have a pendulum, let's say, yeah? So this pendulum is swinging, yeah? And of course, let's say that you're applying a force to this pendulum. If, let's say, the pushes that you're giving to the pendulum, if it is, let's say, at certain times, of course, if it matches the frequency of the pendulum, then of course the pendulum start to swing, let's say, with a larger amplitude. When this happens, we can say the system is in resonance. What does it mean? That means the natural frequency, or let's say the frequency of the vibration matches, let's say, the frequency of the natural system. Or let's say when you give it a push, that is basically, you can say that is a vibration, that is a frequency. Yeah? If that frequency is equal to the natural frequency of this pendulum, then of course this pendulum will be set in resonance, which in that case, of course, the amplitude of the swing will become, let's say, larger and larger and larger. All right, so of course, we can say, once again, we can say resonance is a phenomenon that occurs when the frequency of the force applied to the system matches the natural frequency of the system, let's say, of the vibration of the system, you can say, resulting in what? Resulting in a larger amplitude of vibration. Now take a look, we have a study tip, you need to know this one. What does it say? It says in resonance, the amplitude increases, which makes the vibrating object to swing what? Bigger and bigger and bigger until it collapses, for example, if this push continues over and over, let's say. That is, for example, like a bridge, all right? Or it could be like a stadium. Now, the second tip that we have, it says, at resonance, remember this, right? When something is resonating, we can say the frequency of the force applied is matching, or it is equal to the natural frequency of the system, you can say. And of course, the third tip that we have says the resonance is a special case of forced vibration. Now remember, do you remember what was forced vibration? We said when you set one of the pendulums in motion, the other pendulums start to move or start to oscillate because of this one, yeah? So of course now that is called forced vibration. These pendulums did not want to vibrate, let's say. He did not give them a push, he just gave a push to this one, but then this vibration transferred through the elastic band, let's say here, this loose elastic band to the other pendulums. Now they are forced to swing back and forth with this one, let's say. That is basically what is called what? What is called forced vibration here. So we can say, but remember this, because these two, by the way, so what exactly happens here when this one here, let's say you set this pendulum in motion, this one has the same frequency. This, let's say the first blue and then the second blue, yeah? So once you give a push to the first blue pendulum, all the other pendulums start to vibrate with it. But remember this is very important, because this pendulum's length is the same as this one, so we can say the frequency of this pendulum is the same. Right, the frequency of this pendulum, or natural frequency of this one, it is going to be the same as the frequency that is this pendulum is, let's say, vibrating or swinging with. And of course now, so these pendulums will be set in motion or vibrate, but because these two, you can see here, the So we can say these are swinging, that is a forced what? Forced vibration, you can say. All right, but these two are or have the same frequency. So we can say this would force this one to vibrate, but because the frequency of the vibration of this one matches this one, so what will happen? Now the amplitude of this one here starts to get increased, or it gets bigger and bigger and bigger, and in turn, remember this, the energy of this one, of course, would get less and less and less. Why? Because this energy would be transferred to the other pendulum here. So we can say this, the second blue pendulum here, right, would start to oscillate because it is forced by this one here. But, all right, because the frequency of this one matches this, or these two are, their frequency matches. So of course, now this one would move with a bigger amplitude compared to all that. And of course, this was one of the Wizari questions here. It says, when one of the blue pendulum is set in motion, which one of the other pendulums, of course, would swing with the largest amplitude? And of course, is going to be this blue pendulum here, or you can say the second blue pendulum. Why? Because it is frequency matches the frequency of the first blue pendulum here. But these two are going to vibrate, but of course, not with a big pendulum here. All right, so of course, resonance in some cases could be useful, in some other cases could be harmful or destructive, as a matter of fact. Yeah. So for example, energy is transferred from one pendulum. This is the reason what happens there. All right. So the amplitude of the vibration of the first blue pendulum will decrease, and of course, so we can say because of the transfer, or you can say because energy is transferred. So remember this, the first blue pendulum will decrease, that is the amplitude we're talking about, right? And the amplitude of the second pendulum will increase here. And of course, there is more into this. You can say if one of the pendulum is set in motion, only other, let's say blue pendulums, of course, whose length is the same, will eventually oscillate with a large amplitude. Or once this happens, we can say this amplitude, this pendulum is resonating. That means it is in state of resonance. All right, so of course, take a look at these examples. These are one of the side effects of resonance, you can say, yeah. Of course, it could be destructive. Resonance can lead to a disaster. That is, as you can see in the pictures here, of course, we have in 1940, the Tacoma Narrows Bridge in Washington, of course, collapsed due to what? Due to winds creating what? Creating a standing wave leading to a structural resonance. And of course, let's say this wind, let's say, of course, now wind can cause a push, let's say, to the bridge. And of course, this push, let's say, that is basically a forced vibration, let's say, or forced, let's say, frequency. And if this, the push of the wind, if it matches the frequency of the bridge, and of course the bridge then, in this case, it will start to swing, let's say, with a larger and larger amplitude until, of course, at a point where the bridge can no longer, let's say, oscillate with a bigger amplitude. That is the point where it can collapse. Because remember, these are the structure of this, yeah? These are, of course, metal, solid stuff, so they can, it's not like an elastic band that can swing forever or something like that, yeah? So at a certain point, of course, they will collapse. Similarly, another case like that, that is during 1989, that is Loma Prieta, you can say, earthquake in California, which is a freeway's upper deck collapsed. Why? Because of the earthquake waves. There was, let's say, an earthquake, and of course this earthquake's vibration matched the upper deck of this highway, let's say, bridge. And of course, once the frequencies are matching, then what happens? This bridge, of course, or the system would vibrate with a larger amplitude. This larger amplitude or back and forth movement, of course, would lead to a collapse. And of course, this is what happened. So let's say collapsed, or you can upper deck collapse, as the earthquake waves matched at its natural frequency, which was about, of course, 1.5 hertz, you can say, creating or causing resonance. All right, now we have a question here, says what? Under what condition does resonance occur, yeah? So remember this, we said resonance occur when the, let's say, when the frequency of the vibration matches the natural frequency of the system. When this happens, the system will be set in, let's say, or the system will be in resonance, okay? So once again, resonance occurs when the frequency of the applied force, right? When the frequency of the applied force, in this case, matches the natural frequency of the system. That is when resonance occurs. Now, we have another question, says, why are pushes given to a playground swing more effective if they are given at a certain regular intervals than if they are given at random positions in the swing cycle. Now, in order to help you understand this better, I have something to show you or demonstrate perhaps. We can say, all right, let me get this. All right, so let me get something. This is basically something, you can consider this as a swing, yeah? So for example, let's say now we give, let's say, or we just set this swing into motion, yeah? So imagine this. If every time that this, let's say, consider this a swing, yeah? All right, so this is more likely a pendulum, but you consider this as a swing. So every time if it comes back to me here, if I give it a push, what do you think will happen to the amplitude? Of course, it gets bigger and bigger and bigger, yeah? So what happens if I give it a push, for example, when it comes back right past the equilibrium? What happens if I do this, for example, if I give it a push here, for example, every time it comes back, if these pushes are not, let's say, at regular intervals, of course, this vibration is not going to be, let's say, or the system is not going to be in resonance. In this case, the amplitude will not be large as, for example, as it would happens here. So when will it be more effective? Of course, it is more effective when this, let's say, swing is in motion, and of course you're giving it a push, let's say, at regular intervals. So it has to be at certain times, for example. It has to be, let's say, doing this when this, let's say, swing comes back to me here, then I'll give it a push, because when I do that, the amplitude gets larger and larger and larger. But if it is not back yet, so if I give it a, let's say, let's try it again, for example, right? So now if I give it a push at regular time intervals, you can see here, now this, if I don't let it swing here, all right, so you can see here, now the amplitude can get bigger and bigger and bigger. Yeah, this one is elastic, so you can see that it's bouncing a little. But imagine what happens if these pushes were not, let's say, at regular intervals, for example. Yeah, it goes back and forth, so on every time you can push it at a point here. Yeah, and of course this would, affect it, or you can say the amplitude will not be large enough. So going back to this, why it will be more effective if these pushes are given at regular intervals? That is because when the average pushes or forces match the frequency of the swing, then what will happen? And of course, the swing's amplitude will increase to maximum here. If not, of course, you would see that the motion of the swing would be not as pleasing as it should be, let's say. All right, so another question that we have says, although soldiers are usually required to march together in steps, and of course that is what they're supposed to when we see them marching, yeah? But they must break their march when crossing a bridge, right? So when they are crossing a bridge like this, for example, they are asked or required to break their march, not to move all together in step, let's say, yeah? All right, that is basically when they move in step together, that is called marching here. So explain the possible danger of crossing a rocky bridge without taking this precaution. Like what would be or what might go wrong if they all pass or cross a bridge and they are moving in step as well. In this case, their step, right, of course, that is a force, that is a push, might cause a vibration. And if the vibration of their footstep, let's say, matches the frequency of, let's say, or natural frequency of the bridge, what do you think will happen in this case? Of course, resonance happens. The bridge start to oscillate with a bigger and bigger amplitude, and that might cause damage or cause the bridge to collapse. All right, so this is why soldiers are required not to march when they are crossing a bridge like the one in the figure shown. All right, so we have section review now. What does it say? It says, a tuning fork consists of two metal prongs. That would be a tuning fork, you can see, two metal prongs that vibrate with a single frequency when struck lightly, all right? What will happen of a vibrating tuning fork if a vibrating tuning fork is placed near another tuning fork of the same frequency? Explain, yeah? So remember this, once this tuning fork is struck, of course now it is going to vibrate with it, yeah? And of course these vibrations will pass through the air, and then of course we'll go to the second tuning fork, yeah? But these two, because they say they have the same frequency, so what do you think will happen? Now this tuning fork will vibrate with, or because of this one, of course, with a larger amplitude. You can even hear the sound of this tuning fork. Inshallah, next time perhaps I'll show you a video how it is done, let's say, or how this vibration can be transferred to the second tuning fork, and of course then it can set this, let's say, this tuning fork into resonance, and of course you would see that. So to make it short, the vibration of this one will be transferred to the second tuning fork. The tuning fork or the second tuning fork will vibrate forcefully, and once they do that, because this vibration matches the vibration of this, So this tuning fork will be set in resonance, or it will resonate, you can say. So the tuning fork will pick up the vibration of the first tuning fork, right? And a faint sound will be heard from the second tuning fork. And this happens, or this occurs, because both forks have the same natural frequency, which is the condition, let's say, required for resonance. All right, now we have another question. It says, critical thinking. What do we have in here? It says, which of the following factors change when sound, or when a sound gets louder? Remember, when a sound gets louder here, so basically we're talking about, let's say, the amplitude, the intensity, or you can say the relative intensity as well. That is one, yeah? And then for the second part of this, it says, which will change when a pitch gets higher. Remember, pitch is related to the frequency, yeah? So let's see which one of these, or what will happen when the sound gets louder. So we can say when a sound gets louder, will the intensity change? Of course, because you can say intensity, right? That means, or you can say directly proportional with the amplitude. So in this case, the louder the sound, that means the larger the amplitude, which in another way, the larger the intensity as well. What about the speed of the sound? The speed of the sound, because it is the same medium, or given the same medium, so the speed of the sound doesn't change at all here, right? What about the frequency? Remember, the sound gets louder. It's not like the pitch is changing, so the frequency doesn't change here. That is for the loudness. What about the decibel level? We do know that the decibel level is related to the intensity, and of course the relationship was logarithmic, yeah? So in this case, of course, we can say the decibel level will also change. What about the wavelength here? The wavelength, of course, it will not change. Why? Because the pitch, the frequency doesn't change. If the frequency doesn't change, that means the wavelength doesn't change also, because these two are inversely proportional. All right, what about the amplitude? And of course, because the sound is louder, so of course, that means a bigger amplitude. So we can say the amplitude is, or will also change. So which one of these factors change when a sound gets louder? The factors that change is the intensity, the decibel level, and of course the amplitude as well. These three factors will change. Now, what about the second part of the question, which says, which change when the pitch gets higher? Remember, we said pitch is related to what? Frequency. So higher pitch, that means higher frequency, yeah? If the frequency is higher, what do you think will happen to the wavelength? And of course, the wavelength would get lower in this case, yeah? Because these two are inversely proportional. So let's take a look. Will the intensity change? That is not. What about the speed? Remember, since it is the same medium, the speed will not be affected in either cases. So the speed is not going to change at these conditions at all. What about the frequency? We said higher pitch, that means higher frequency. So frequency does change. What about the decibel level? It doesn't change. What about the wavelength? And of course the wavelength changes as well, because we said the speed doesn't change. Remember, speed equal to frequency times wavelength, yeah? So this one is constant. If the frequency is increasing, the wavelength must decrease. So these two, of course, are inversely proportional. So these two will change. What about the amplitude? Because it is just the pitch, so the amplitude is not going to change. So remember, the things are what change when a pitch gets higher? It is only the frequency and wavelength. All right, so what is next? Now, take a look. We have some national exam questions. It says, a phenomenon that occurs when the frequency of a force applied to a system matches the natural frequency. Whenever it says matches the natural frequency, that should be, or one thing should come into your mind, and that is what? That is resonance. Once again, just to double check with this, it says a phenomenon that occurs when the frequency of the applied system matches the natural frequency, and of course that is resonance. Take a look at the second one. It says what? Which of the following factors will not change? Yeah? Remember, will not change when a sound gets louder. Remember, when a sound gets louder, we said what are the things that can change? We said the intensity change, the decibel level change, and of course the amplitude will change as well. Yeah. So any other things, regardless to these three, of course, let's say doesn't change. Yeah. So we have speed of the sound. Remember, speed of the sound doesn't change. What about the intensity? The intensity change, the decibel level change, the amplitude change as well. So the correct answer here that doesn't change, of course, it is the speed of the sound. Now, question 3 says, which of the following factors change for a sound source when a pitch of a sound gets higher? Remember, we said if a pitch gets higher, pitch is let's say, related to the frequency, higher pitch, higher frequency, lower pitch, low frequency. So that means the frequency will change. And don't forget, if the frequency is increasing or decreasing, of course, that affects the wavelength. So we can say if the pitch change, the frequency and wavelength will change as well. So which of the following factors change, right, if the pitch or when the pitch of a sound change? Can we say the amplitude? No, amplitude is related to the loudness. What about the speed of the sound? We said as long as it is the same medium, the speed of the sound won't be affected. What about the decibel level? That is also, we can say, related to the loudness, sort of like logarithmic function, of course. So one thing that gets changed for sure, or certainly, that is the frequency. All right, and so the last question here says, which of the following factors change when a sound gets louder? We went through this, yeah? So the intensity, the amplitude, the relative sound intensity of a sound, and all the answers are correct. And in this case, the correct option would be option D here. All right, now, a new section, and that is, of course, section 4.3, harmonics, okay? So what are harmonics, you can say? Harmonics are, we can say, are those frequencies, let's say, that are produced when strings are, let's say, plucked. And of course, in order for this, let's say, strings with different wavelength, let's say, of course, or different length can produce different frequencies, let's say. And of course, we can call these harmonics. That's one thing you can say. So, but in order to go through this, let's say, string, or you can say standing waves on a vibrating string. Yeah? So remember, let's say, the chapter, let's say, vibration and wave discussed like how when a string is fixed, both ends vibrate, various standing waves can form, let's say, yeah? And of course, in musical instruments like what? Like the violin, these vibrations create multiple standing waves, of course, with different wavelengths and frequencies simultaneously. Thus, even seemingly a single pitch sound from a string instrument comprise multiple frequencies. So we can say, even if we have a single string, let's say, we can have, or let's say, or generate different frequencies. And of course, by increasing or decreasing, let's say, the length of the string, that is one. Or you can say, sometimes you just have one, let's say, string, but of course, let's say you just put your finger right on a point on that string. So of course, the length of the string that vibrates would change. And of course, that causes a different, let's say, or the generation or the creation of a different frequency. So now the simplest vibration that can occur when the distance of one node, let's say, when the distance from one node to the next is always what? Is always half a wavelength. And of course, the string L must equal to half a wavelength, you can say. That's a wavelength is twice the string. So take a look here. Now we did talk about standing waves, yeah? So let's talk about perhaps standing wave a little bit. Do you remember what was standing waves? We said we can have standing waves when two waves, right, that are passing through, let's say, the same medium in opposite direction, but these two waves, they have exactly, or they have the same frequency, wavelength, and amplitude. So when these two pass through a given medium, of course, standing waves will be formed, yeah? And of course, let's say these standing waves would be the result of constructive and destructive interferences. And if you do remember, we said we have nods and antinods, yeah? And of course, at the end of the strings were nods, and then some other points would be antinods. Nods were those points that there is, let's say, minimum vibration or zero vibration or displacement, you can say, while antinods were those points with a, let's say, we can say, the highest point or points with a maximum vibration or displacement, you can say. And of course, we said, in order to have, let's say, the minimum wavelength for standing wave, we had something similar to this, let's say. So we did talk about this one here, and of course we are talking about this one too, yeah? Let's say the minimum, all right, the minimum wavelength, or you can say the maximum wavelength actually. So let's say, actually, so we have, let's say there's a string here, yeah? And of course this string would be, these are the ends of the string you can call, what do we call these? We call them nods, yeah? And of course this is knot as well. And this point here you can, we called it antinod. And of course you do know that the difference or the distance between, let's say, one knot to another consecutive knot, it was just half a wavelength, yeah? So if this is, you can say, this is the length of the string here, Or how do we know this is half a wavelength? You can also see that, let's say this is, if we start from this point all the way to the other end, that is only one wavelength, yeah? So what we have here is just half of this, you can say, yeah? So, or if not, you can go ahead with the number of amplitudes. This is one amplitude, this is two amplitude. We have a total of 4 amplitudes, yeah? So this is 3 and 4. So if we only take this two here, that is half what? Half a wavelength. So we can say the length of this string here equals to what? Equals to only half a wavelength. All right, so half a wavelength. So if you cross multiply, we can say the wavelength equal to 2 times the length of what? The length of the string. This L stands for the length of the string here. So we can say this wavelength here would be the maximum wavelength, let's say, of a vibrating string, or when a string vibrates with what? With, let's say, 2 knots with 1 anti-knot here. So we can call this one here the maximum what? The maximum wavelength here. So what is the maximum wavelength for a string when it vibrates with, let's say, on a standing wave, you can say, then the maximum wavelength is going to be 2 times the length of that. Remember this. All right, what happens when we, let's say, when we have other, let's say, vibrations, let's say, or standing waves? We can have something like this, for example, yeah? And of course, now here we can have 1 anti-knot, 2 anti-knot, and 3 anti-knots. This has to be, like at the end of this. So of course, in this case, we have 2 anti-knots, yeah? So this is 1 and 2 here. So you can see here that on a string here, the number of knots is always 1 more than the number of anti-knots. And of course, we said if you're given the length and the number of anti-knots, you can always find the wavelength, yes? If you remember the equation, yeah? What was the equation? We said basically wavelength equals to 2 times the length divided by the number of anti-knots. If you know the number of anti-knots, if you know the length, you can always find the wavelength of that wave, let's say. All right, so now remember this. This is the maximum wavelength of what? Of, let's say, the wavelength for a string that is vibrating. But remember this. How about the frequency? You do know that frequency and wavelength are inversely proportional, yeah? So if the wavelength is maximum, what about the frequency? The frequency here is going to be minimum, or you can say the frequency of this vibration, right? The frequency of this vibration is going to be what? Is going to be minimum here, right? So minimum. All right. So, but we have something, like to find this one here, or to find the frequency there. We do know that speed of a wave equals to what? Equals to frequency times wavelength, yes? All right, so we're trying to find the frequency, let's say. So frequency equals to speed of the wave divided by wavelength. But we said wavelength here equals to what? Equals to 2 times the length. So we can say speed of the wave is divided by 2L here. That is for what? That is, you can say, for the minimum frequency. The minimum frequency for a standing wave, let's say, that is basically called the first harmonic, or fundamental frequency, you can say, yeah? All right. So what if I want to find the second one here, right? For the second one here, there are another way to do that, you can say, yeah? We can say, and by the way, using this, we have another equation now, right? Let's say, in order to find the frequency of a vibration, let's say, of a string, we can always use this. So let's say Fn, all right? We'll talk about this one as like more, but let's just say Fn equals to n times, let's say, V divided by 2L, all right? So this, what does this n means? This n is basically, you can say, number of what? Number of harmonics. Number of harmonics. So what are harmonics? You can say harmonics are an integral multiple of the fundamental frequency. So we had the fundamental frequency. Fundamental frequency, we said it is equal to what? Equal to V over what? Over 2L. And of course, we can add 1 here if that is the fundamental, you can say. But 1 times this equals to the, like the same thing. So speed of the wave divided by 2L here. What if it is, let's say, the second, by the way, now we can call this one the first harmonic, right? Now we can call this one the second harmonic, but these are all for, let's say, a string here. Remember, these are for strings, you can say. And of course, the strings are, you can see the 2 ends of the string are always, let's say, taught to the ends of this, or you can say fixed here. Of course, we would have, like vibrations like this. For the second harmonics, we can have something like this. All right, so something like this. So in this case, we can say, by the way, using this one here, we can say n, all right? Using this equation, we can say n times v over 2l, yeah? But if we're talking about the second harmonics here, this n in this case just becomes 2 times v, let's say, divided by 2l here. If you don't want to use this, you can always use something better, yeah? First, once you find the fundamental frequency using, let's say, 1 times, this is times v over 2l, once you find this one here, all right, then the rest, finding the rest of the other harmonics would be very, very easy. So how, for example, let's say second harmonic, we can just say 2 times the fundamental frequency, because all the remaining of the equation will be the same, except then you're changing one thing, which is this number of harmonics. So you can either write the equation, or if you have the fundamental frequency, you can just multiply, let's say, 2 times the fundamental frequency. What if you're trying, or you want to find the fifth, let's say, harmonics, the F5 in this case? We can say F5 equals to 5 times the fundamental frequency. So whatever the number of harmonics, remember, for strings, we can always multiply that number to the fundamental frequency. You will see that will be the same for a pipe that is open at both ends as well. That would be the same case, yeah? But for now, I just want you to remember this. We have something called fundamental frequency, yeah? So what is fundamental frequency? We can say, which is represented by F1, by the way, right? It is the lowest frequency of a vibration of a standing wave here. So once again, what is a fundamental frequency? It is the lowest vibration of a standing wave. So this is, you can see, it is a standing wave, yeah? So we said that if this is the whole thing is length, of course, we can say the wavelength equal to 2 times this. So wavelength here will be maximum, but the frequency will be minimum. So minimum, or the lowest frequency of a vibrating, let's say, a standing wave, that is basically called fundamental frequency. All right, take a look here. It says, these study tips are very important. What does it say? It says if a string vibrates with 2 knots and 1 anti-knot, the wavelength produces maximum. This would be useful for multiple choices. For example, let's say, when will a let's say the wavelength of a vibrating string would be maximum. One of the options, of course, would be, let's say, when the string vibrates with 2 knots and 1 anti-knot. That is the case where the wavelength is maximum, the frequency is minimum. What if they say, for example, when the string vibrates with, let's say, 3 knots and 2 anti-knots, that is not the maximum wavelength, yeah? Or let's say they can give you any other numbers. Let's say the string is vibrating with 10 knots and 9 anti-knots, yeah? So these are the numbers, but remember this, in order for the wavelength to be maximum, the knots and anti-knots on that string, it has to be 2 knots and 1 anti-knot only, because the 2 ends would be knots, and of course this one is going to be anti-knot. And don't forget, okay, the distance between one knot to another is just half a wavelength, yeah? What if it is from 1 knot to, let's say, an anti-knot? That is basically going to be a quarter of a wavelength, you can say. All right, speed of the wave, which is equal to what? Equal to frequency, or wavelength times the frequency. If you're trying to find the frequency here, frequency equals to what? Equals to speed of the wave, of course, divided by the wavelength. And then after that, remember this is the maximum wavelength, or you can say the wavelength for the fundamental frequency, yeah? Or the fundamental, let's say, vibration here. So in this case, we can just, after having this, we can substitute this here into the equation, of course. So we can say the fundamental frequency, speed over lambda, speed is, like the same in this case, let's say, and then, but lambda here equals to 2 times the length of the string. So of course now, fundamental frequency equals to what? Fundamental frequency for string, that is, for string, you can say it is equal to what? Equal to V over 2 times the length here, okay? Now that is the fundamental frequency. Take a look at this question, which is also very important. It says, the wavelength of the fundamental frequency, the what? The wavelength of what? Of the fundamental frequency of a vibrating string of length, let's say of length L is equal to what? Remember this. Now, if you forgot about this, you can always redraw this, yeah? This is the fundamental, let's say, you can say, frequency or vibration here. And the whole thing is basically L, yeah? So remember, we have nods and another nod here, and there is one antinod here. So what is the wavelength equal to? We do know that the wavelength equals to what? All right, let's erase this. We do know that the wavelength of this, all right, let's say string or vibration equals to 2 times the length. Why? Because we do know that the distance between one node to another, that is just half a wavelength. So we can say if this is half a wavelength, then 2 times this, of course, equal to 1 full wavelength. If not, you could do this, let's say, you can say basically L equals to half a wavelength, yeah? And then cross multiply wavelength equal to 2 times the length here. So which one is 2 times the length here? And of course that is option D here. All right. Now we have something called harmonic series, yeah? So now we did learn about, we did talk about fundamental frequency. So what is the fundamental frequency? The lowest frequency of a vibrating, let's say a vibration for a standing wave, yeah? Remember, when the frequency is the lowest, the wavelength is the maximum here, don't forget, yeah? Now we have something called harmonic series, yeah? So not only the fundamental, we can have a series of frequencies, yeah? So what is harmonic series? It is a series of frequencies that include a fundamental frequency, that is 1, right? So harmonic series, it includes the fundamental frequency that we've covered, and what else? And an integral, or you can say integral multiples of that fundamental frequency, all right? So for example, we have the fundamental frequency, and of course we name it F1, yeah? So harmonic series would be an integral multiples of that fundamental. So for example, let's say the second harmonic, that is going to be 2 times the first one, yeah? So we said earlier, let's redo this one again. So we said fundamental frequency is equal to F1, and of course F1 was equal to V over what? 2L, yeah? That is basically fundamental frequency. Now harmonic series, we're talking about, when we say harmonic series, we're talking about F1, the fundamental frequency, and also integral multiples of what? Multiples of fundamental frequency. In another way, we can say 1 times F1, yeah? Or 2 times F1, or 3 times F1, yeah? Or 4 times F1, and of course it goes on, yeah? So these are called what? These are called harmonic series, which is basically the fundamental, or the frequencies that include the fundamental frequency, and of course integral multiples of what? Of fundamental frequency. All right, then of course now we have something else called harmonic, yeah? What is harmonic? That is going to be the integral number or integral multiple of what? Of the fundamental frequency. Now we can have something like this, yeah? So we can say Fn equals to what? N times F1, yeah? So of course now you can say this N, that is basically the number of harmonics, you can say. So what is harmonic? It is an integral multiple of fundamental. So now we have this equation here. Remember, if you want to find the first harmonic, we can say F1 integral multiple of that. If it is the first harmonic, N in this case is going to be 1. 1 times what? 1 times the fundamental frequency. What if we want to find the second harmonic? By the way, this is called first, this is called second, third, fourth, and it goes on like that. So second harmonic, we'll say N is going to be 2 because it is second, so 2 times the fundamental. Third harmonic, remember these are 4 strings, don't forget. We can say 3 times the fundamental frequency. All right, so, and of course you can see here what we have as well. Using, how do we know it is equal to this? We can use this equation, because fundamental frequency equal to 2 times the length, yeah? If it is the fundamental, that is going to be the first, we can divide by N. This N is standing for number of what? Number of harmonic, which is also equal to, you can say, number of antinodes as well, as you can see here. How many antinodes do we have? It is just 1. So we'll say 2 times the length divide by 1 here, you can say. All right? Or we can say number of harmonics. Here, it is the first harmonic, so we can just have 1 here. Here, second harmonic, or you can see here we have 2 antinodes, so you can divide by 2 to find the second harmonic. So the wavelength the wavelength for the second harmonic, using this equation, we can say second wavelength equal to 2 times L, that is something fundamental, yeah? Then what a change is this number of harmonics. So if it is the second one, we'll just divide 2L divide by 2. In this case, we can say wavelength for the second harmonic equals to the length of what? The length of the string here. What if it is the third harmonic? What would be the wavelength of the third harmonic? So all you have to do, just use the equation again. Third harmonic, we said, yes? So we'll say 2 times the length. That is something doesn't change, yeah? The only thing that it changes is the number of harmonics. So if it is the third, right, you can put 3. Fourth, put 4. Third, let's say fifth, put 5. And then, of course, it continues like that. So these are to find what? To find the number of the wavelength in every harmonic, let's say. All right. So based on this, we can say harmonic series, remember this is also very important, based on what we have covered, we can say the equation of the fundamental frequency can be generalized to include an entire harmonic, which is of course Fn equals to n times F1 here. So now to generalize this, let's say even more, we can say harmonic series of standing waves on a vibrating string. Don't forget. Right? Remember this equation because you will be asking exams, of course. So we can say Fn equals to n times 2L times V, my bad, right? Times V over what? Over 2L. And of course, this n represents number 1, 2, you can say 3. These are whole numbers of, or you can say integral multiples of what? Of, let's say, or just integral multiples, let's say, of course. So remember this equation. In the next video lesson, of course, we're going to solve some questions regarding this one, yeah? But remember this, Fn stands for what? Stands for, let's say, the frequency that is nth harmonic. And of course, this n number of harmonic, V, that is the speed of, you can say, the speed of what? The speed of sound, of course, that is in air, you can say, which is measured in meter per second, you can say. What else do we have? Or you can say, by the way, the speed of, we can say, what do we have here? All right, we can say this, the speed of the vibrating string, by the way, right, not the speed of the resultant sound wave in the air, which is measured in meter per second. The length represents the length of the, or L represents the length of the string, which is measured in meter. If it is not in meter, make sure you convert that. All right, so next time we'll continue from question 22, which says, what is the fundamental frequency and how are harmonics related to the fundamental frequency? So, till next lesson, make sure you keep practicing, and of course it's very important to go back to the, at least to where we started with harmonics. Make sure you understood the whole concept, and of course keep practicing. Till then, keep practicing. Assalamu alaikum wa rahmatullahi wa barakatuh.